Hi everyone! In today's video, we're going to be going over Hooke's law and spring force. So let's qualitatively look at spring force before we get into any formulas. So we know that before we push or pull a spring is resting at a position which we can call equilibrium or position 0. If we push on the spring, we feel a push backwards against our hand. If we pull the spring, we feel a pull backwards on our hand. In AP Physics 1, we use the idea of an ideal spring which obeys Hooke's law. Hooke's law states that the force of a spring exerts is proportional to the displacement from its equilibrium or 0 position. So, if this is the equilibrium position of a spring, the x would be the displacement from that equilibrium that we pull or push it. And this negative here symbolizes that the force is always opposite to the direction that we pull. So if we pull the spring this way, the restoring spring force is going to be this way, and vice versa. The next thing that we need to know is the K value of a spring. The K value basically tells us how stretchy a spring is, or how easily we can stretch or push it. This isn't the formal definition, but it is a good qualitative way of imagining what the K value represents. The units of K are always in newtons per meter, and that is because the unit of our force is in newtons, the unit of our displacement is in meters, so meters times newton per meter is equal to Newton. Hooke's law of K delta x tells us that the restoring spring force has a linear relationship with the displacement that we pull or push it. For example, in this graph, if we have our force versus displacement graph, where force is on the y-axis and displacement is on the x-axis, we can find our K value. If we have force and we have delta x, at force divided by delta x is equal to K. Therefore, the slope of our graph will give us the K value. So here, our slope is going to be 20 divided by 0.1, and that's going to give us a K value of 200 newtons per meter. Okay, so now that we know the basics of Hooke's law and spring force, let's put this idea into practice with a few different problems. So our first problem says, a mass of 25 kilograms is suspended on a vertical spring. The K value of the spring is 150 newtons per meter. How much did the mass stretch the spring? Okay, so the first thing we do is to draw a picture of this scenario. I often draw a before and after picture in order to help find out the displacement from the equilibrium position. So let's say that before the mass was hung, our spring had an equilibrium position right here. Our mass was hung and it stretched the spring, oops, that's a really bad picture, and it stretched the spring some distance below the equilibrium position. That means that this is the x we're looking for. If the mass is suspended, that means the restoring force of the spring has to equal to the gravitational force of the mass. If the spring force is also equal to kx, we can solve for x by dividing mg by k, and this gives us x. And because all three of these are known values, we simply can plug this into the calculator. So 25 times 9.8 divided by the K value of 150 gives us a displacement of 1.63 meters. Our next problem says, a group of physics students run an experiment to find the K value of a spring. For each stretch distance, the students record the restoring force and plot their data on the graph below, where y is the force and x is the displacement. If the students hang a 10 kilogram mass on this same spring, how much will it displace? Okay, since we're given a graph of force versus displacement, we can find the K value by taking the slope of this graph. So I would choose the points 0, 0, and 0.05 and 10. Using a calculator, I'm given the slope of 200, and our units will be newtons per meter. This tells us that the K value of a spring is 200 newtons per meter. Okay, the next part says that the students hang a 10 kilogram mass on this same spring, and we need to figure out how much it displaces. So this is kind of similar to the last problem. If a mass is hung on the spring and is suspended, the restoring force of the spring has to equal to the gravitational force or the weight of the mass. Since we already know K and we know that the restoring force is equal to K delta X, we simply have to do mg divided by K to find the delta X. So let's plug this into our calculator. 10 times 9.8 divided by 200 gives us a displacement of 0.49 meters. Our next problem says, a force of 300 newtons is required to stretch a spring 20 centimeters. How far can a force of 250 stretch it? And the 250 is supposed to have the newtons there. Okay, so let's call the force of 300 newtons force 1, and the force of 250 newtons force 2. We know that force 1 divided by the K value is equal to 0.2 meters. We need to know what force 2 divided by that same K value is equal to. We can say that the K value here, because the K value is unknown, is equal to force 1 divided by that 0.2 meters. Therefore, the displacement by force 2 is essentially 0.2 times the force 2 divided by force 1, and that's going to give us our delta X. So let's plug these into the calculator. 0.2 times 250 newtons divided by 300 newtons gives us 0.16 meters, and that is the displacement of 250 newtons. Okay, so this is our last practice problem for this video, and although it's multiple choice, it is a little bit difficult conceptually. So, two massless springs of spring constants K1 and K2 are hung from a horizontal support. A block of weight 12 newtons is suspended from the pair of springs as shown above. When the block is in equilibrium, each spring is stretched an additional 24 centimeters. Thus, the equivalent spring constant of the two-spring system is 12 newtons divided by 24 centimeters, which equals to 0.5 newtons per centimeter. Which of the following statements is correct about K1 and K2? So, from this, I'm going to use the picture that they already drew. And what usually helps when you have two parallel springs is to draw a box around them and first imagine them as one spring. In order for this one spring to hold up the 1.2 kilograms, the K times the displacement has to equal to 12 newtons. We already know that the displacement of the two springs together is 24 centimeters. If one spring displaces 24 centimeters and the other displaces 24 centimeters, that means the block is basically displaced 24 centimeters. That means the K value is the 12 newtons divided by the 24 centimeters, which equals to 0.5 newtons per centimeter. So that was kind of the proof of how they got the equivalent spring constant. But now let's take a look at how each spring is acting independently. So we know that one spring with a spring constant of K1 times the displacement of 24 centimeters plus a spring of K2 times the displacement of 24 centimeters have to add up to a force that totals to 12 newtons. If we factor out this 24 centimeters, we're left with 24 times K1 plus K2, which equals to 12 newtons. Looking at the answer choices, I noticed that there's K1 plus K2 as an answer choice for D, and we already have a K1 plus K2 here. So I would isolate for K1 and K2, and we get K1 plus K2 equals to 12 newtons divided by 24 centimeters, which we got as 0.5 newtons per centimeter. This answer satisfies the question D. So as a result, if we have two springs that are parallel or next to each other, they act independently of each other. So you can add up the forces together. If they're, for example, holding a mass up or suspending a mass, you can find the displacement of each spring. If they have different K constants, or the force that the two springs need to add up together to suspend a mass. So generally, two springs that are in parallel like this question add up to suspend the mass or act the net force on the object together. Thank you so much for watching this video. In our next lesson, it's going to be our last dynamics lesson, and we're going to be combining all the things we learned into one tough free response question. So springs, pulleys, and incline all in one FRQ in one system. So that'll be in our next video. I hope this video helped. Thank you.